Hey, good afternoon, one and all. So it's still me, shaved off my head. It's a Corona cut, so don't get confused. It's still me, and we are doing the lecture. I'm at home, so due to this lockdown and all, we are not going to college. So this week, at least, as per the directive, we are going to do the lectures and everything from the college, from our home itself. So I'm going to share my lecture. This is going to be the lecture number 5. So today is 26th of April. I think you can find out the slide here. It is visible, I guess. So what we are going to do today is we are going to see the very important topic. So every exam this is mostly asked either directly or indirectly. So what we are going to do today is the second order electrical system modeling. So last day we have done the electrical system modeling, but that was also for the second order circuit. The circuit was in loop. So there was two capacitors in that circuit, and I have posted the video lecture. I did not intentionally post the PDF because PDF and the lecture, whatever is there in the video is same. So I wanted you to listen to the lecture more than have the PDF. So obviously after the end of this module 1, I will post all the written materials and there will be no short of material. And whatever book you have, that is the book of M. Gopal, there you can find out. So maybe not in the first chapter, but in the second chapter, you'll find a lot of theory or a lot of different solved numericals on how to find the electrical transfer or electrical system transfer function. But whatever we are going to do today is this is a very basic of all the mathematical modeling, and we are going to see a second order electrical system, and we will see a second order mechanical system, and we will find out what is the relationship between them. So very important question, because it is said that all the very big systems, maybe it's a 10th order, 15th order, 20th order system, that means there are many energy storing elements, but all those elements, all those very big systems can be represented as a equivalent second order system. So whenever there is a very big building, we cannot show the very big building to everybody. So what we do is we make a small model. Okay. Though the small model is not having every feature of that building, but what we try to do is we try to accommodate or we try to make the small system at least similar looking like the big system. So why am I giving you this analogy? Because whenever I am saying second order electrical system, so it may be a uh, 30th order of electrical system, but we can still model it with the help of a second order electrical system. It may be having some errors. So whatever features and dynamics of the 30th order system, second order system will be having a lot less dynamics than that. But it's a second order system can be called as a very coarse or very rough kind of model of a bigger order system. So electrical system, mechanical system, everything you see. So today we're going to introduce some of the mechanical components, and numerical is asked for mechanical system transfer function as well as for electrical system transfer function. So mechanical system is generally having output as displacement. Will be having the relationship between them. So this lecture is very important. Every lecture is important, but these topics are very important. So try to understand, because whenever we are going to see unit step response of second order system, so it can be mechanical, it can be electrical likewise. Okay, so I'll be going forward. So these are the topics. First, I will do RLC system modeling. So whenever I'm saying RLC system modeling, you have already seen the system. It is the same system or circuit. We don't call it circuit anymore because we are into control system. So I'll be calling it system. So what is the feature of system? There will be some system components. Here, three components are there: R, L, and C. They are called discrete component. Two of them are energy storing element. That is inductor and capacitor, L and C. We will be finding what is the transfer function of RLC system, and we have to find out what is the characteristic equation. So it will be output by input. Denominator of the transfer function is called as characteristic equation. So whatever polynomial is found at the denominator of transfer function, that equals to 0. That is the characteristic equation. That is the most important equation for any system, because from the characteristic equation we can find the position of the pole. And if we are finding that poles are all situated in the left hand side of S plane, that means poles are all negative with real part, negative real part. So poles can be imaginary, the value of S. So it's a quadratic equation at the denominator that can be having imaginary root a plus jb. So the real part we have to see. If the real parts are having negative real part for all the poles, then the system will be stable. So all these things I'll be telling you repeatedly. At present you might not understand, but yes, as we keep on going ahead, as I keep on giving you more examples, you'll be able to understand. So main thing is we are supposed to find out transfer function first thing. Second thing, from transfer function we have to see what is the denominator equation. Denominator equation is nothing but called as characteristic equation of the system. Third thing is, from the characteristic equation we are supposed to find what are the poles of the system, that is what are the roots of the characteristic equation. And fourth thing, we have to find out the pole position, roots of the characteristic equation. There is a pole and we have to see whether the poles are having real part as negative or not. If the poles are having real part negative, that means poles are stable pole. Stable pole means what? If the system is stable means what? So that thing we will see in the consequent lectures, because I told you this control system is all about three things. First is gain, stability and energy. So more is the energy, more is the gain of the system, and more is the gain or more is the energy of the system becomes more unstable. Okay, so for every system we are trying to find out the analogy or analysis of stability, pole position and all those things. So all the stability and pole positions can be found out only if we know what is the pole position. Pole position can be found out from system transfer function, and transfer function gives characteristic equation. From there we find pole position. So this is the relationship of all parameters. So we are going to see the electrical modeling, that is called as V. V stands for input voltage, and mechanical system input is force. Okay, so mechanical system is generally given by capital F. Electrical system is generally given by capital V. So then we will see force voltage analogy, which is called as FV. That means what is the interrelationship between mechanical and electrical system. And then there is another analogy which is called as FI, okay, which is called force current. So force current analogy, that means mechanical and electrical, and force voltage analogy. An electrical system again can be modeled in two ways. It can be having input as voltage or it can be having input as current. So mainly we are going to see three systems today: electrical system with voltage as the input, an electrical system as a current as an input. Okay, same system RLC, but for RLC series circuit we will find that voltage is given as the input. For RLC parallel circuit we will see current is given as the input. So if it is RLC parallel circuit, then what is the equivalent mechanical circuit for that? That is called as FI analogy, that is force current analogy. If voltage is the input, that is RLC series circuit, then what is the relationship between RLC series and mechanical system? That is called NP analogy. So all these things are there. So this is lecture number 26th. Sorry, lecture number 6. This is 26th of April. Lecture number 5. I'm going to open the PDF that I had done last day. So from the PDF we will see what is the mechanical system modeling and what is the electrical system modeling. Just give me a time. I'll be just taking some time to open the PDF document. So whatever things, experiments or whatever numericals are done in the class, please prepare that thing very properly, because every lecture is cumulative in nature. So whatever things are taught last day, that is the electrical system and how to find the transfer function of the electrical system, all those things you should prepare very properly. Okay, so I will just open the PDF what we had started last year. So this PDF I will upload in your Google Classroom as soon as I finish the topic. So in the PDF we had done the electrical system modeling example. Okay. I'll open that PDF. I think the PDF is visible to you. Okay, so I'll be explaining it from this PDF, so I'll make it big. The same thing will be shared to you. Uh, is it clear enough? Can you see all the things in the PDF clear enough? All the equations and
Yes,
everything?
sir.
Okay. So the same numerical we had done last day. So the same numerical we had done last day, that is I had given you two loop circuit. So there were two resistors and one inductor, one capacitor, and we found what is the transfer function. So V2 is the output voltage and V1 is the input voltage. So this such 3-4 examples are there. It is written with me. I have the PDF. So today I will upload that in your group, and I want you to practice all the four numericals given in the PDF. In the same line it is. Okay, so it is not possible to do it in the class. Every simple thing cannot be done in the class, but yes, it is very neatly done, and I'll upload the PDF today itself. And you just check, practice all those numericals. Any doubt you are having anytime, please send me the message, sir, I'm not able to understand this. So we can have a Google Meet, or over phone I can discuss the things to you, and we can get it cleared. So today I will upload some solved numerical on electrical system modeling. The method is the same whichever we had discussed last day, but there are different flavors. Now what we are going to do is we are going to change the branch a little bit. So from electrical we are going in the mechanical domain. Okay. So this is in mechanical systems, the motion can be of two types. One is linear, that is translational motion, and another is rotational motion. So for our syllabus, both these two things modeling are there. So rotational motion means you can say it's a DC motor or it's a AC motor or something. Okay. So motion is rotational motion is having inertia. Okay, for linear system, now if you are having pen and paper, you must have pen and paper and calculator with you. If you don't have, please get one. For linear system, the inputs are first I'm giving you force. Okay, the mechanical system I'm giving force and I'm getting displacement. So now the golden rule of mechanical system, we are giving force and we are getting output as displacement. So force is given by F. In Laplace domain it is called as F of S, and displacement is given as capital X of S. Okay, so displacement is xt in time domain, capital X of S is the output displacement. So force is causing the displacement, so displacement is the output, force is the input. So if I want to make the transfer function or find the transfer function, it will be between xs divided by fs. So x is the output, f is the input. So if it is electrical system, just now we have done RLC circuit, we are giving voltage, you are getting current. So transfer function can be between is by vs. So is is the current, vs is the voltage. So current is the output and voltage is the input. Or current can be represented as rate of flow of charge. So I can be given as dq dt. Okay, so I can be given as dq dt. That is rate of flow of charge is nothing but current. So if you are substituting current as the rate of flow of charge in the circuit, we can find transfer function is charge divided by voltage. So voltage we are giving, that's why charge is created. So charge is the output, voltage is the input. So charge by voltage is the transfer function of electrical system. Similarly, displacement by input force is the transfer function of the mechanical system. Now it can be linear motion, linear force, or it can be circular force. If it is a motor or something, it is a circular force, and if we push something, it's a linear force. So both the systems are there in our syllabus. We will be solving both types of numerical, that is for linear or translational motion and rotational motion. So in some mechanical system, the motion I'm reading from here, in some mechanical system, the motion can be combination of linear and rotational both. In that case, finding transfer function becomes a little tricky, but you can do that. So equations that govern the motion in such system are directly or indirectly related to Newton's law of motion. So Newton's law, there are three laws. First law of motion, it says that it's inertia. So whatever, if there is a subject or if there is a matter, material, if we push it, it will keep on moving. It will keep on getting displaced forever as long as it is not having a reverse some motion which is stopping its forward motion. So this is the inertia. If we push some object, it will keep on moving in that direction forever. So why don't we move like that? Because there is air pressure, there is friction at the base. So at the time, friction and air pressure, they are causing an opposite force. That's why it cannot move forward forever. Okay, that's the first law. Second law is equal to F is equal to m into a, that is force is equal to mass into acceleration. And third law we all know, if we give some motion, if we give some force, not motion, if we give some force, it will be experiencing an equal and opposite force. So these are three laws which are governing all the mechanical system components and principles. Now let us see, as we are having RLC in case of electrical system, what are the mechanical system components? So mechanical system, first component is mass. Okay, mass is just a mass. Okay, mass means any weight. Okay, so I'm having my mobile, so this is also having mass, so this is a mechanical object m. Okay, so it is the property which stores a kinetic energy or translational motion. So mass cannot store potential energy. So mass always stores kinetic energy. Okay. So displacement of mass always takes place in the direction of the force applied. So whichever direction I am pushing it, it will move in that direction. So that is mass. Displacement of mass always takes place in the direction of the force applied. If force applied is Ft, okay, so here the F should be small actually. F of t, it produces the displacement of xt. So force is the force is given in the forward direction, and it is getting displaced in the forward direction as xt. So this should be ft actually, because time domain we represent it in small. So this should be small ft is equal to m into d2x dt2. Can anybody tell me, or can you understand that this is the Newton's second law? What is d2x dt2? X is nothing but displacement. What is dx dt? So this is something you should write down. That is, if x is displacement, dxt dt is velocity, and d2xt dt2 is acceleration. Do you know this? All of you, can you just confirm? If x is displacement, dxt dt is velocity, so you can write it down, and d2xt dt2 is the acceleration. So do you know this at least? Any of you, can you confirm?
Yes, sir.
Okay, so Abrar is saying, and you are saying that you know it. So x is displacement, dxt dt is the velocity, and d2xt dt2 is the acceleration. So here you are finding force is equal to, so this force is small f because it's continuous force, it's a continuous domain parameter. We can find its Laplace transform, then we will represent it as capital F of s. Okay, as it is written here, capital F of s is equal to m of s square. From where this s square comes? Because d2xt dt2, so this is acceleration. So force is equal to mass into acceleration. Unit of mass is kg. Okay, so unit of mass is kg, or you can say gram. So there are different systems, cgs, fps, mks, all those systems are there. So we know that unit of mass is kg. Okay, so m per s square, meter per second. So acceleration is meter per second square, that is correct, and mass is given by kg. So what is this thing? Kg meter per second square, that is nothing but Newton. So kg meter per second square, kg into meter per second square, that is nothing but Newton. Now here, this is how the mass movement is shown. So this is the mass, and this is having some wheel below. That means this mass, whenever it is dragged on the surface, so this is the surface, this sign is called as fixed surface. Okay, so force is applied here. So force can be pushed or force can be pulled. Okay, here the pulling force is shown here. So this mass m is pulled in this direction, this is called ft, and this will generate a displacement of xt. So this is called as the diagram. Okay, like we are having circuit diagram, mechanical systems are having diagram. This is the diagram. So force is causing the displacement, and because of wheel there is no friction here. If I don't show the wheel, then you have to show a friction. So another force component will get added here. So be very careful. If you are drawing mass with wheel, means there is only one component, fs is equal to ms square xs. But if I don't show this wheel, that means between mass and surface there will get another force in the opposite direction, which is called as friction force. So which will be in the opposite direction, so it will be called as b of xs. What is that? We are going to see in the next case. Okay, so mass without wheel and mass with wheel, in both cases the modeling will be different. So what is meant by modeling? Whatever is the mass thing, we are trying to represent it by an equation. So what is that equation? F of s. So it's in the Laplace domain. F of s is equal to m into a square into xs. So m into a square is coming because this is double derivative. That's why a square is coming, and xt and dt. So that's why it is becoming xs. Okay. So Fs is equal to m s square xs. Then there is linear spring. So this is the third, actually. This is the, okay, fine, let us do it in the second thing. So what is, so somebody is asking some question, let me, okay, Abrar is saying yes, fine. What is spring? We have all seen spring inside our pen. So in your pen, whatever you are using, you don't see spring, but previously the push button pen kind of thing, they are having spring inside. Or you can see the shock absorber of your vehicle, that is car or scooter or bike. Or if you are traveling by a train, when the train comes very close to station, or inside station it is in the platform, there are very huge kind of spring which is just connected in front of engine. There are two springs like this, and they are connected to a spring, and they just contacted like this. Or if you're just standing some point and one train is passing very slowly, you can find that above every wheel of the train there is this thick, this very big springs are connected. So whenever there is spring, there is coming some shock, and spring actually absorbs energy. And what we will find is the spring is equivalent to the capacitor of the electrical circuit. So in electrical circuit, whatever capacitor we are finding, C, so spring constant K is equal to 1 by C. The spring is equivalent to capacitor, but not directly C, but 1 by C. We will see that. So spring is like a belt or electric cable of certain stiffness. So spring constant is given by stiffness. Spring can be, it can store potential energy. Okay. So here above we have seen that the mass, it cannot store potential energy. Mass always moves in the same direction of the force applied. So mass cannot store potential energy. But in this case, you will be finding that the spring, it can store potential energy. There are two types of energy, kinetic and potential. Okay, so force required to cause displacement is proportional to the net displacement in the spring. So what is the thing? So we are giving force as Ft, and it is K into Xt, where K is called as the spring stiffness constant. Now if you are finding the Laplace transform of that, what you will be finding is Fs is equal to K into Xs. In the previous case, we found F was equal to m into d2x dt2. That's why there had come a s square here. So F is equal to ms square xs. But in this case, as Ft is equal to k into xs, that means this is the spring. One end is connected with the unmoving wall. The other end is pulled by force Ft. So this spring will get elongated. So whatever is this term, this point, this will get elongated. Okay, so that elongation is called as the displacement. So Ft is equal to K into Xt. So in the Laplace domain, you will find this Fs is equal to K into Xs. So this is the thing. Now, a special case, write it down if you are having pen and paper. That suppose there are two masses. Okay, and this is mass 1 and this is mass 2. And in between there is a spring connected. Okay, so you can draw this diagram, or you can see my lecture later on, or you can take a screenshot now, and you can write down what will be the spring equation when the spring is kept between two masses, and mass 1 is given with a force Ft. So mass 1 is showing a displacement of x1, mass 2 is showing a displacement of x2. Now the spring is there, and one end of it is having a displacement of x1, another end is having a displacement of x2. At that time, what is the force equation? So this is mass m2, this is mass m1, both are moving. You have to consider that both are connected with wheels. Okay, there is no friction here. So Ft I am giving x1t is one direction force, x2t is x1 is one dimension displacement, x2t is also displacement, but x2t is the displacement of m2, x1t is the displacement of m1. Then there's a spring connected between m1 and m2. What will be the force equation? So here you can see that net displacement is given by x1 minus x2. Obviously x1 will be greater and x2 will be lesser because force is connected directly to x1. Okay, so x1 displacement is more, x2 displacement is a little less. So what is the net displacement of the spring? It is x1 minus x2. So what will be force equation now? Fs is equal to k into x1s minus x2s. So these are very important thing. When there are two masses and one spring is connected between that. So previous case there was only one mass, one spring. The other end of the mass was connected to the wall. At that time F was equal to k into xs. Okay, but in this case, the spring is connected between two masses m1 and m2. Both are moving. So mass m1 is moving with x1, mass m2 is moving with x2. Spring is connected between that. Then what will be the force equation? So force is there. So Fs is equal to k into, now there are two movements, x1 and x2. So it will be x1s minus x2s. Likewise. Last one, which is equivalent to resistance in case of your electrical circuit. So I gave you the analogy of spring. So spring, though it looks like inductance, but no, there is no relationship between spring and inductance. Spring is actually equivalent to 1 upon capacitance, because spring also stores energy, capacitance also stores energy. So spring is an energy storing element. Okay, mass is also storing energy, and this is storing kinetic energy. It cannot store potential energy. So mass will be equivalent to L. Mass will be equivalent to the inductor in the RLC circuit. We will see that. And spring is equivalent to 1 upon capacitor of the RLC circuit. And last component, what we are finding is, it is called as damper or dashpot. What is meant by damper? It is nothing but a piston. So you have seen the door closures. Okay, you have seen the door closure. So there is a piston kind of thing. So one end is connected to the door. You push the door open. Door opens very fast, but while closing, very slowly it closes, because there is a piston. Okay, opening you can push it. So that push is nothing but this Ft. So as soon as you're pushing the door, this piston is coming out, and inside this there is a viscous fluid. So that's why, or sometimes it can be air. Okay, so this piston comes out as soon as you are pushing the door. So mass is generally connected to the this thing dashpot. It is called damper or dashpot. So mass is connected to the damper or dashpot. So as soon as you're pushing the door, the piston comes out very fast, but it doesn't get closed very fast, because we don't want the door to close very fast and create a thudding noise. We don't want that. What we want, opening will be very easy, closing should be very slow. Okay, that is the door closer. So behind every door, in the offices and all, towards the top, in our GIT, we the boys toilet and all these things, you can see, I think in the girls toilet also those things might be there beside the door. So there is a door closure, so there is a piston kind of arrangement. Okay, so that is the best example of dashpot or damper. Or if you're traveling by a AC bus, okay, which are pneumatically controlled, which have pneumatically controlled door. Okay, so this kind of damper or dashpot you will find in those pneumatically controlled door. Okay, so backside you will find the closure of that thing is happening very slowly. Okay, so this is the dashpot, and we are giving the force, frictional force Ft to open it, and how it closes. Okay, so as soon as we are pushing it, we are giving some force. Okay, we are opening that door, but the closure of that piston, it flows through a resistance. So resistance occurs because within this piston there is a viscous fluid. So this piston actually enters this fluid, and very slowly it presses the fluid, viscous fluid or air, and then comes to the ending position. So whenever we try to open the door, we press the door, this piston comes outside. Okay, and whenever we are leaving it, this piston goes inside this socket or chamber very slowly. Okay, this is actually what is called as dashpot. And as soon as I'm pushing it open, I'm causing a displacement xt. Okay, and how it moves in the opposite direction, rate of xt. So initially this movement will be very fast. It is going towards, as soon as you leave it, so you apply the force and leave it. So initially this piston will move very fast, and gradually its speed will reduce as it is going towards the initial position. So that's why you will find that friction is equal to b dxt dt. So whenever there is a motion, friction exists opposite to the direction of motion. Viscous friction means this piston is filled with viscous fluid. So viscous friction constant is given by capital B, which is equivalent to resistance in electrical circuit. So I will tell you, for electrical equivalent of this mechanical systems, mass is directly proportional to inductance. You can write down all this. Second thing, this viscous friction constant, that is Ft is equal to B dxt dt, or Fs is equal to Bs xs. From where this S is coming? Because this is differentiation. And we have told that all initial conditions we are assuming as zero, because this is a transfer function method we are trying to apply. So we are not taking what are the initial conditions of if there is any energy stored inside it. Anyway, this is a element which is not storing energy, because mass and spring, they store energy. Okay, this damper does not store energy. So this is B dxt dt, but we're not considering any initial condition here. So Fs is equal to Bs into Xs. But the same thing, this end we are considering, so left end of the B, that is the dashpot or damper, we are assuming it to be connected to the wall. Not necessarily it can be connected to another mass. So right side can be connected to mass m, left side of B can be connected to another mass m2, and then how is it? We can see that in the numericals. So whenever there is a motion, friction exists in the opposite direction of motion. Viscous friction constant is given by B. It has linear relationship with the relative velocity between two moving surfaces. Friction is shown by dashpot or damper. So friction is shown by dashpot or damper. What is meant by that? It means that F frictional. So whenever the door is closing, at that time it is getting closed with respect to the friction. Okay, so that friction is given by friction forces F T. Obviously, it should be small f, B dxt dt. So Fs is equal to Bs xs. Likewise, now what we are saying is the same thing. Friction between two moving surfaces. Is it visible? Is it visible to you that there are two masses m1 and m2, and between that this dashpot or damper, it is connected. So it is nothing but a piston. Okay, it is connected between m1 and m2, and m1 is so the force, I have not shown it, it's my mistake, I'm sorry. The force is connected here with m2, the same pulling kind of force. Okay, there is a f2 force here. Okay, and due to f force, m2 is having displacement of x1. Okay, and m1 is having displacement of x2. Okay, so the net frictional force F is equal to B dx1 dt, because force is connected to m2, so that's why this is the main force, dx1 dt. And next is this is the force of m1. So this will be this side will be having some displacement x2, the right side also will be having some displacement x1. So what is the net frictional force? Ft B of dx1 dt minus dx2 dt. Now if you are taking both the Laplace transform, dx1 dt is x x1s, dx2 dt is s x2s, and B is the frictional constant. So that will be s x1s minus x2s. So what it is saying is force applied as mass m2, which is related to displacement x1, is always greater than displacement x2 force applied to m1. That means the same thing I told you, that the force I have not shown here, my mistake, I'm sorry. So force is applied to m2. Okay, then x1 is higher displacement and x2 is lower displacement. x2 is the movement of mass m1. So in this case, what we find is net frictional force Fs is equal to Bs x1s minus x2s. So friction between two moving parts are different, and damper stores some potential energy. So in rotational system, linear friction is converted to torsional friction and given as B. So we will see whenever we are doing rotational system, we will see how the systems actually behave. But before we are going for rotational system, let us find out a mechanical equivalent circuit. Okay, if anybody is having any doubt, you can ask, you can raise the question in the chat box, or I'll be going to the next part, that I'm going to combine all these three systems. Okay, MBK, and this is shown like this. It is shown like this. And there is another way of showing it. I think it is given below. Okay, it is not. So here is a more complex two-stage system, but generally in your exam or very basic thing, this is a MBK system. So as we are having LRC, that is inductor, capacitor, and resistor system, in mechanical we are finding a MBK system. There is a mass, damper, and spring. So in that case, x1t is the displacement, because ft is the force which is given towards the from the top to bottom. So it is pulled down. Okay, this is the direction. Hence, x1t is the displacement. So input is f and displacement is x1. Now, in the right side, whatever diagram is given, it is called as a free body diagram. It is called as a free body diagram. Okay, so in that case, you are finding x1t is a node point. Okay, so x1t is the output equation, output parameter. So x is the displacement, which is the output parameter, and which is caused by the force F. So as you are finding in case of electrical system, we are giving voltage as the input and current as the output, and we are finding current at the nodes. So okay, KCL says that I1, I2, I3, these are the three currents coming at the node. then net algebraic sum of node currents equal to 0. Same thing happens here. Okay, so here at this point is a node x1t. Okay, their three components are connected in parallel, M, B, and K. And net effect, whatever is the input voltage or whatever is the input force and whatever are the stretches and all those things in this together, net effect will be 0. So we can prove that. So right side, this thing is called as a free body diagram. Okay, free body diagram of MBK. Now there is another, and we can find out what is the transfer function of this. Okay, check the second system. Okay, you understand these two diagrams and it will be enough. Are you with me, all of you? MBK system, is it understandable? Hello? Okay, so Akshata is saying it is okay. So now I'm going to show you a two layer of MBK system. So now be careful, it is not only MBK, it is M1, B1, K1. So this is the M1, B1 and K1. These are three things. Okay, and again the force is given from M2 towards below. This is the main force. Okay, main force is coming from M2 towards below. Okay, so next is, this is the MBK. This is the first layer. So this is the first layer which is attached to the base, or which is attached to the ground. So this is M1, B1, K1 system. Then this is M2. So this is M2. And M1 and M2, they are connected with B2 and K2. So B2 and K2. Okay. So B2 and K2 is the link between M1 and M2. So between M1 and M2, the link is, so this is M1. You can interchange. So these two things in parallel, you can write B1 first, K1 next, M1, doesn't matter. Okay. But M2 is coming like this. Okay. So now you are finding that this is the first node 1. Okay. X1, which is this point, and right side this is M2. And here parallel to M2 you can show another block, and you can show that this is F. So F is coming in parallel with M2. Okay, so this whole system can be represented like this. So what is B2 and K2? K2 is nothing but spring 2, K1 is spring 1. So K1 is the spring 1 constant. B1 and B2, there are the dampers, and they are the damper constants. M1 and M2, their mass in kg. So you can see here B1, B2 and K1, K2 are under displacement x1 and x2. So what you are finding is here two things you have to see. This B1 and B2, top side they are having displacement x1, bottom side they are having displacement x2. So you can find out B1 and B2, they are subjected to two displacements. Right side displacement is x2, left side displacement is x1. So these are very important things that you have to understand. Whereas B1, K1 and M1, left side is kind of connected to wall and right side is connected to displacement x1. So this is very important thing you have to understand. B1, B2 and K1, K2 are both under displacement. So K2 and B2 are under displacement of x1 and x2, whereas K1 and B1 is only under displacement of x1. Mass M2 is under displacement of x2. So mass M2 is under displacement of x2, whereas mass M1 is under displacement of x1 alone. So these are the bottom things you have to understand. Okay. So likewise, it will be going on. I will show you the detailed numericals on this. So this is, let us first do what is the force voltage analogy, and I will do it from this understanding. So now what I'm doing is I'm combining all these three systems. Okay, all these three systems are combined now. Okay, all these three systems are combined. You can find there's a mass. Okay, and there are different configurations. There are different way it can be represented. So there is a mass here, and there is a B here, which is nothing but a spring. Which is nothing but a damper, and there is a spring here. Okay, and whatever diagram was given above, that means this first diagram, whatever first diagram is this MBK, and whatever the bottom diagram is this, okay, MBK. These two diagrams are same, because in the previous diagram in one side I had shown a wall. So this means it is connected to wall. They are not moving. So bottom there is a wall and top there is a wall. Okay, likewise. So if you consider this B connected to wall, so you can take it in parallel also. So it is the same thing. Only I have made a wall as 90°, and that is the only difference. Okay. So MBK system, now given input, so now concentrate, this is the main part we are entering. Given force is Ft. Okay, so Ft is the force that I'm giving, and it is actually equal to Ma. Ma is mass into acceleration. Aishwarya, please mute your video. Aishwarya, Aishwarya K, please mute your video. Thank you. Okay, so FT is the force given. Now this force is doing three things. Whatever we are doing in case of electrical circuit, whatever voltage we are giving, it is creating three voltage drop. Voltage drop across inductor. It's okay, Aishwarya. Voltage drop across inductor, voltage drop across capacitor, voltage drop across resistor. So the same force, whatever we are giving for mechanical circuit, it is creating displacement in three components. First is the displacement across mass, second is the displacement across damper, and third is the displacement across spring. That means the net force is wasted in three parts. First is F is equal to m into A, that is mass into acceleration, plus B is the resistance or friction into velocity, okay, B into V plus K into xt. Okay, so now if you are trying to find out the Laplace transform without any initial condition, that is equal to, so A is nothing but d2x dt2, where x is the displacement. So here I am giving supply as ft. So whatever voltage supply we give in case of electrical circuit, in the mechanical circuit we give supply as force, and this force is causing displacement xt for all these three components. So mass is moved by xt, damper is moved by xt, and the spring is also moved by xt, but in one direction, because the other direction, other side is fixed. Okay, that side is having displacement of 0 because that is fixed to wall. Now I am finding force is equal to ma plus bv plus kx. Okay, A can be represented as d2 xt dt2, V can be represented as xt dt, dxt dt. Now you are finding the Laplace transform. So if you are finding the Laplace transform, F is equal to ms square plus bs plus k. Why there is a s square? Because there is a double derivative. Whenever there is a double derivative, so d2 xt dt2 means if there should be a 2 here, d2 xt dt2, then means s square of xs. dxt dt means s of xs, and kxt become kxs. So is this equation understood? Whatever is given here, fs is the force given in Laplace domain. So previously it was small ft, now it is capital Fs, is equal to ms square plus bs plus k into xs. So what is the transfer function now? Transfer function will be output upon input. So output is displacement, input is force. So this will be xs by fs. That will be equal to transfer function 1 upon ms square plus bs plus k. That is the transfer function of mechanical system. I'll repeat again. If you have pen and paper, you can write down. So output is xs, that is the displacement. Input is fs, which is nothing but force. In this case, the mechanical system transfer function will be output upon input. That is xs divided by fs. That is equal to right side 1 by ms square plus bs plus k. Now ms square plus bs plus k is equal to 0 will be the characteristic equation of the system. Okay. Same thing you find in case of electrical system. What happens? So I think this circuit is very well known to you. So remember, what is the mechanical system transfer function? X by F is equal to 1 upon ms square plus bs plus k. Same thing you can check for electrical system output. So Vt is the input, R, L, and C are the systems or system components. So you can directly write down Vs equal to R plus Ls plus 1 by Cs into Is. Okay, so Is again further can be written as dqt dt. That is, current is equal to rate of change of charge. Then Is becomes SQS. Now here Is you substitute with SQS. So what you find is Vs equal to Ls square plus Rs plus 1 by C. That is inside it. Okay, take the S there. So it becomes Ls square plus Rs. Okay, RCS plus 1 by C. So take S here. Ls square plus Rs plus 1 by C into QS. So whenever you are substituting SQS, here, so IS you are substituting as SQS, this S and this S gets cancelled. This S gets multiplied with LS becomes LS square, and this S gets multiplied with R. So it becomes LS square plus 1 by C of QS. So what is the input in case of electrical circuit? Vs. What is the output in case of electrical circuit? It is QS. Okay. I'll be stop presenting and I'll shift to my PPT now. Okay, so the PPT is there. Let me just show you the PPT. We are having almost kind of 10 minutes in our hand. So in that 10 minutes, we will do what is called as the FV analogy. That means what is the force voltage analogy of the system? We'll see that. Okay. Like this, I will enlarge it. Okay. Now this is the presentation. So I think presentation is visible. First two slides I had already shown you. This is the third slide. So is it understandable? Vs equal to Ls square plus Rs plus 1 by C. The same thing. Supply you are giving, and you are finding Vs equal to R plus Ls plus 1 by C into I. So for our derivation, because here I is not equivalent to whatever we found in case of mechanical circuit. So mechanical I had shown you previously. Mechanical I had shown you previously. What is that? Fs equal to ms square plus bs plus k into xs. There is no s here. Okay, so this is xs. So whatever is xs in case of a mechanical circuit, the same thing is qs in case of electrical circuit. So can anybody tell me what is the equivalence of output parameter of mechanical circuit and electrical circuit? And second question is, what is the equivalent of input in case of mechanical circuit and electrical circuit? So such questions are asked in the IA. So this is called as mechanical to electrical system analogy. What are the output input parameters in case of mechanical? So mechanical input parameter is force. What is the input parameter in case of electrical? It is voltage. So that's why this analogy is called as force voltage analogy. Samely, what is the output quantity in case of electrical? It is charge, Qs. And what is the output quantity in case of mechanical? It is force, that is excess. Okay, sorry, it is excess is nothing but displacement. So now you can find here Vs equal to Ls square plus Rs plus 1 by C into Qs. Now take this Q as the output to the numerator, take this V at the denominator. So what is the transfer function I'm finding? 1 by Ls square plus Rs plus 1 by C. So the same very small whatever equation you are finding. So just take this part Ls square plus Rs plus 1 by C at the denominator. So output upon input, that is charge upon voltage, equal to 1 by Ls square plus Rs plus 1 by C. Now what is that? Take this L at the denominator. So numerator, there is a mistake, it should be 1 by L. Okay, and this should be S square plus R by L plus 1 by Cl is equal to charge by input voltage. This is what you have to remember. So output upon input, that is charge by input voltage. So what is the characteristic equation? Characteristic equation will be S square plus R by L into S plus 1 by Cl is equal to 0. S square plus R by L into S plus 1 by Cl is equal to 0. So this is going to be the characteristic equation of second order system. Okay, second order electrical system. How can we say that it is second order electrical system? Because we are finding the order of the denominator characteristic equation is equal to square. S square. That's why the whole system is called as a second order system, or transfer function is called as a second order system transfer function. Now why this is second order? Because there are two energy storing elements. Which are the energy storing element? L and C. So everything is falling into place. So there are two energy storing element, L and C. That's why order of the system is S square. Okay, resistor does not store energy. Resistor is non-energy storing element. Output is charge, input is input voltage. Check the mechanical system. I give you this equation, Fs equal to ms square plus bs plus k is equal to xs. So you are finding xs by Fs equal to 1 by ms square plus bs square plus k. Now here also I have divided the numerator by m. So there is a mistake in the numerator. It should be 1 by m, and denominator should be s square plus b by ms plus k by m. What is xs? Xs is nothing but displacement. What is Fs? Nothing but input force. Okay, so whatever is charge in case of electrical circuit, same thing as displacement in case of mechanical circuit. Whatever is the input voltage in case of electrical circuit given by capital V, same thing as force in case of electrical circuit. Oh, sorry, mechanical circuit. This is called as FV analogy. That is force voltage analogy. Last slide for today. What you are finding is comparing the equations. So what are the comparing equations? Here you can find is Ls square plus Rs plus 1 by C. This is the denominator equation. Ls square plus Rs plus 1 by C. In mechanical, what you are finding is Ms square plus Bs plus K. So just see these two equations. Ls square plus Rs plus 1 by C and Ms square plus Bs plus K. So L becomes equal to M, B becomes equal to R, and K becomes equal to 1 by C. So if you are comparing mechanical and electrical, the denominator or the characteristic equation is For mechanical, ms square plus bs plus k. For electrical, it is ls square plus rs plus 1 by c. If you're comparing this, what you're finding is L is equal to m. Whatever is the inductor in case of electrical system, that is mass in case of mechanical system. Whatever is the resistance in case of electrical system, that becomes friction P in case of mechanical system. And whatever is the spring in case of mechanical system, that becomes 1 by C. So if you see the transfer functions, here it is K, ms square plus bs plus K. But for electrical system, it is 1 by C, because we know from where 1 by C comes. So it is 1 by C integration of IT dt. It is not C integration of IT dt. It is 1 upon C integration of IT dt. And because of integration IT, it becomes 1 by CS. So that S is here, that S gets cancelled with the S of QS, so it becomes 1 by C. So for electrical system, it is Ls square plus Rs plus 1 by C. Mechanical system, it is ms square plus bs plus k. If you are equating it, you are finding inductance L is mass m, resistance R is friction B, capacitance 1 by C is equal to spring K. Voltage is the input quantity in case of electrical, that is V. Force is the input quantity in case of mechanical, it is F. Now the most important thing, what is the output quantity? Output quantity for electrical is Q, that is charge, unit is coulomb. Output for mechanical system is displacement, that is given by meter. Are you with me? If you're with me, a last point, sixth point, which is not mentioned in here, write down. What is dq dt? Can anybody tell me? What is dq dt in case of electrical circuit? If charge is q, what is dq dt? What is the parameter called in electrical?
Change
Current,
in
sir.
charge.
Change in charge. What is dq dt?
Change in charge to the change in
Current.
time.
Current. Current.
Madam, that is called current. It is written here. Check. It is equal to dq dt. Understandable? Okay. So what is dq dt? It is current. And this is displacement. What is dx dt? What is dx dt?
Velocity.
Rate of change of
Displacement.
displacement with respect to time. What is that thing called?
Distance.
dxt
Velocity.
dt. What is that? It is called as velocity. Check here. Okay. So last point here in write down FV analogy. Last point you can write down. Last point, that is dq dt. That is current is equivalent to dxt dt. That is velocity. So that sixth point is not written here. Before uploading the slide, I will add it. So last point, point number 6. So this question is asked for 10 marks. That give me the analogy between force voltage analogy for electrical and mechanical system. So last point, sixth point, you have to write down dq dt is I, or dqt dt is I, that is current, and dxt dt is the velocity. So whatever is the current you are finding in electrical circuit, that is equivalent to charge in mechanical circuit. Is it understandable, everybody? So Q we are writing Qt, and xt we are writing. So dqt dt is nothing but the rate of change of charge, that is current, and dxt dt is the rate of change of displacement, that is nothing but velocity. So these are the six different things. So five I have given here. Sixth you have to write dqt dt and dxt dt and complete the table. So this I have given you the relationship between force, voltage. Now you can convert this FV into FI. So whenever current you are inputting to LRC parallel circuit, then also this mechanical circuit can have its equivalent with the FI circuit. So how to do that? I will record that in 10 minutes and I will upload. So I'm stopping here. You can leave the session, but FI analogy 10 minutes recording I will do and I'll upload with this session. Thank you. You leave the session. Okay, so this is mechanical to voltage analogy. This is called as FV. So don't consider the rotational thing here. So I'm still finding there are 8 students. Please don't miss lecture. If you are having any other lecture, please join that. Okay, so this is translational. There is a linear movement, and this is the electrical, and this is FV analogy. So what is that? The force is equivalent to voltage. Mass M is equivalent to inductance. Friction constant B, that is B dxt dt. So friction is equivalent to resistance. Don't see the middle column. Middle column is for rotation. We have not done that. We are doing linear movement. There is a translational movement of mechanical into electrical. Then next is spring constant, is spring K is 1 by C. So K is 1 by C, we have seen. Displacement is nothing but X in mechanical is equivalent to charge in electrical. And last point, dx dt or dxt dt, we can equivalent it to current. Okay, so that is I is equal to dq dt. This is called as force voltage analogy, but obviously the force is translational force. Now let us see what is the Fi analogy. Now you have seen two circuits. One is series RLC circuit. So that was in the previous circuit. Now you can keep all the R, L and C in parallel. So this is a different circuit. This is a different kind of modeling. So whatever MBK system, mechanical system, the same MBK system can be made equivalent to Fi as well. So F stands for force, mechanical, and this is a current analogy of the same circuit. What is the current analogy? It is nothing but I have to give the current as the input. So it's a time varying current, and that is L, R, and C. Okay, so L, R, and C both are connected in parallel. And here there is a node, and Vt is nothing but the node voltage. So previous case, whatever circuit was there, electrical circuit, in that case you could say that supply voltage is equal to Vr plus Vl plus Vc. That is nothing but Kirchhoff's voltage law. So that supply voltage input is equal to Vr plus Vl plus Vc. Now in this case, Fi analogy, what I can say is whatever current I am giving, which is at node, this node, you can give any name, that is equal to IL plus IR plus IC. So total current is equal to inductive current plus resistive current plus capacitive current. Now we should know what are the currents. So at this point, node voltage is assumed to be Vt, which is nothing but the output voltage. So what is the resistive current? Resistive current is Vt by R. It is shown here. Okay, so this IR is nothing but Vt divided by R. Okay. What is the inductive current? So these are the equations you should know. Inductive current is 1 by L integration of Vt dt, node voltage integration of that with respect to time multiplied by 1 by L. So this IL, okay, so previously we knew VL is equal to I dit by dt. Okay, what is that? VL, that is inductive voltage, is equal to L, that is inductance, into dit by dt. That is inductive voltage is equal to inductance into differentiation of inductive current. So if you just rearrange that, you will find this inductive current is equal to integration of inductive voltage. Now in this case, all the three components, voltage across that is Vt. Okay, so what is inductive current? Inductive current is nothing but 1 by L inductance of 1 by L integration of Vt into dt. So that is IL is equal to 1 by L integration Vt dt. IR is Vt by R. And what is the capacitive current? So we know the equation, that is Vc is equal to 1 by C integration of IC dt. You differentiate both the sides and take shift C. So what you will find is IC is equal to C into d VCT dt. So this is the same thing we are finding. So now what we are doing is we are representing the electrical circuit in terms of current components. So previously we had represented a resistive circuit in terms of voltage components. Vt was the input, and we are taking the output across capacitance. Okay, possibly, and we are finding what is the current flowing through the circuit, IT. So Vt was represented in terms of IT. In this case, IT is being represented in terms of Vt. So we have changed the input and output parameter. So in this circuit, IT is the input parameter, and Vt is the kind of output parameter. Now Vt also will replace Vt by some other parameter, okay, by using Faraday's law. So IT is equal to IL plus IR plus IC. So IT is equal to 1 by L integration of Vt, that is the inductive current, plus Vt by R resistive current plus C dVt dt. That is nothing but the capacitive current. Now you join all these things because we know from Kirchhoff's current law, that is at any node all the output currents are is equal to same as input current. So input current is IT, output currents are IL, IR, IC. So IS, that is the total current. IT has become IS now. So this IT should be small I. Okay, now it has become IS is equal to 1 by LS. Why 1 by LS has become, why S has come at the denominator? Because this VT is integrator. Integration gives S at the denominator. So it is 1 by LS plus Vt has become Vs at the output side. We have taken common. 1 by R is 1 by R. Okay, and this C dVt dt. So differentiation gives you a S. So this is CS and this is Vs. Okay, so Is is now equal to 1 by Ls plus 1 by R plus CS integration of Vs. Substitute. Now here is coming the new law. As in previous case you substituted current as dq by dt. Current you had represented in terms of rate of change of uh, charge. Okay, so I was equal to rate of change of charge. In this case what you do is voltage is equal to rate of change of flux. And what is the rule? Rule is nothing but Faraday's law of electromagnetic induction. So if there is a flux linkage change, in that case EMF is induced in the circuit. So Vt is equal to d phi dt. In that case Vs is equal to S of phi s. So in this equation Is equal to 1 by Ls plus 1 by R plus Cs. Substitute Vs as S of phi s. So this is very important. And which rule is in this case? Substitute Vt is equal to d phi dt. The rule is Faraday's law of electromagnetic induction. And with that, Vs is equal to S phi s. S comes because there is a differentiation. Now substitute in this equation Is equal to 1 by Ls plus 1 by R plus 1 by Ls into S into phi s. Now this S if you take inside, the Cs becomes Cs square. This 1 by R becomes S by R, and this 1 by Ls becomes 1 by L. Okay, so now what you have to do is you have to find out the output divided by input. So output in this case is phi s, input in this case is Is. So phi s by Is. Phi s by Is will be the transfer function. Phi s by Is will be equal to S square C plus S by R plus 1 by L. Now this has to be made equivalent to ms square plus bs plus k. So this is what is called as current analogy. So in case of current analogy, we are finding that transfer function is phi s by is, because phi is nothing but the flux and that is the output, and is is the input current. So current is generating flux. In case of V and Q circuit, voltage was generating the charge. In this case, current is generating the flux. Generally that happens in case of magnetic circuit, electromagnet. So we give some current and it generates flux. Okay, so Is equal to S square C plus S by R plus 1 by L into phi s. And this is equivalent to Fs equal to ms square plus bs plus k into xs. So if you are finding the analogy between Fi analogy, so current is proportional to force. That is the first thing. Fi analogy, that is force current analogy. That is MBK circuit, whatever I have already shown previously. That is MBK circuit, this circuit, MBK circuit, and the parallel RLC circuit. Between these two, if you are trying to find what is the analogy, what you will find is, first thing, force F is equivalent to current. So current is the input in Fi analogy. This is electrical circuit, but parallel circuit, current is the input. S square C. So capacitor is proportional to M, that is mass. In case of FV analogy, inductor was equal to mass. In the Fi analogy, capacitor is equivalent to mass. In the FV analogy, B was proportional to R. That is, the dashpot or damper constant B was proportional to R. In this case, dashpot B is proportional to 1 by R. So if R is resistance, what is 1 by R? It is the conductance. Okay, so in this case, in case of Fi analogy, mass is proportional to capacitor, and second case, the friction, that is B, is proportional to 1 by R. 1 by R is the opposite of resistance, that is nothing but conductance. And lastly, in that case there was K, constant was K, it was spring constant. Spring constant is now equivalent to 1 upon L. Okay, so L is the Henry, so it is Henry raised to minus 1. So this is the equivalence of Fi analogy. So there are 6 analogies we have seen. What are the analogies here? Force is equivalent to current, input quantity. Displacement is equivalent to flux, that is output quantity. C is equivalent to M, that is capacitor is equivalent to mass. Conductance is equivalent to friction, that is B, and 1 by L, that is Henry raised to minus 1. This is equivalent to what is called as K, that is the spring constant. Last thing, d phi s by dt, d phi t by dt. What is that? Rate of change of flux, that is nothing but voltage. Voltage is proportional to dxt by dt, that is the velocity. So as a 6th point, d phi t dt, that is a velocity, that is a EMF as per as Faraday's law of electromagnetic induction, that is proportional to dxt dt, that is nothing but the velocity. So compare equation 1 and 4, so which is given, you can find out. So here the analogy is given. Capacitor C is mass, 1 by resistance is 1 by R, conductance, that is equal to friction B, 1 by L, that is 1 by inductance, that is equal to spring constant K, current is equal to force, and lastly the flux is equal to displacement. Phi s is equal to xs, that is displacement. Last thing is not given, that is what is d phi t dt, that is nothing but E, that is the voltage, is equivalent to dxt dt, that is nothing but velocity. So whatever chart I show here now, mechanical to Fi analogy. So that is first and third column, you can check. Middle column is for rotational energy, you are not supposed to check that. So first and third column, so F is equal to IT, input quantity, mass is C, friction B is 1 by R, conductance, spring K is equal to 1 by L, that is 1 upon inductance, X is nothing but displacement, here it is flux phi, and velocity Vt, here it is d phi by dt. Note that the series element in FV analogy, that is force voltage analogy, is a series RLC circuit. Mechanical circuit remains the same. The series element in FV analogy get connected in parallel in Fi analogy. Parallel elements in FV are connected in series element equivalent to Fi circuit. So whatever are the series components in FV, that becomes parallel into Fi, and whatever are the parallel components in FV, that connects in series into Fi. So I can give you any mechanical system and I can ask you to convert this thing into equivalent Fi component or equivalent FV component. So that kind of question might be asked in your exam. So far what we have done today is we have seen mechanical system, we have seen two electrical systems, FV and Fi, and we have found out the relationship, mainly 6 parameters, relationship between mechanical and electrical components. And we have known that mechanical circuit can be converted to any two electrical components. Now the last thing, 2 minutes, why do we need to convert mechanical system into electrical system? And all the systems are second order system. Because in mechanical circuit system, we are finding there are two energy storing elements, mass and spring. Okay, friction does not store energy. Mass and spring, they store energy. Electrical, we are finding inductor and capacitor, they store energy. The last thing, why do we need to convert mechanical system into electrical system? Because if we are having a very big mechanical system like a car, okay, we cannot test that in a lab. We cannot bring a whole car and test, convert it into model and test it, not possible. So in that case what we do is we try to find out what is the equivalent thing of that mechanical system, and we can find out what is the electrical equivalent of that mechanical system. So very big mass might become very small value of inductor. Okay, so we can simulate the properties or dynamics of that mechanical system into laboratory by using small electrical components. So that's why there is a analogy. So if we have the mechanical to electrical conversion analogy, what we can do is we can generate very big mechanical model with very small discrete electrical components in the lab, and we can test the performance of big car, not directly, but indirectly in the lab itself. So that's why this mechanical to electrical analogy of the system is very much important. So with that, I conclude today's lecture. Please prepare all these things from the book itself. That is the book of M. Gopal, and that's all. Thank you. You can leave the session now.